Hello everyone, I'm Qinghan Tan. It's my great honor to present our work, PhantomCache Obfuscating Cache Conflicts with Localized Randomization on NDSS 2021. This work was done in Zhejiang University. The whole story begins with a sad fact that cache conflicts will leak information. There are various cache-based attacks such as side channels, covert channels, and researchers have proposed a mitigation mechanism called randomized memory-to-cache mapping, which can prevent attackers' exploitation of cache conflicts. And in our work, PhantomCache, we proposed a new technique called localized randomization to ensure both security and performance. The contributions of our paper are as follows. First, we propose PhantomCache, which shall prevent conflict-based cache attacks through localized randomization. By contrast, previous schemes used global randomization, which is hard to realize and inefficient. Second, we analyzed the key step of conflict-based attacks and proved that existing attacks cost more than 100 years in PhantomCache. This is because PhantomCache increases the key step's difficulty by an exponential factor. Third, we implemented PhantomCache in Champ Sim Simulator and evaluated its performance using Spec 2017 benchmark suites. And it turned out that the average performance loss is only 1.2%. Here is a typical example of cache-based attacks, which is called Prime+Probe Attack. In the figure, it showed a cache set of a 4-way cache. First, the attacker accesses 4 addresses that map to the same cache set to prime the whole cache set with its own cache lines, and then it waits for a period. If the victim accesses some address that map to this cache set during this period, the attacker will observe a cache miss during the probe phase where he reaccesses all 4 addresses and measure latencies. A longer latency will indicate a cache miss. In this way, he will know that the victim has just accessed this cache set. Otherwise, he will know that the victims did not access this cache set. So here we introduce the definition of eviction set. An eviction set is a set of addresses mapping to the same cache set as the victim's address. In the figure above, the eviction set is the 4 addresses of the attacker. So finding eviction sets is a key step in cache-based attacks. First, the attacker begins with a large set of addresses that is guaranteed to have enough addresses to form an eviction set. Then he reduces the set size in a remove and test fashion. He first removes 1 or multiple addresses from the set and then tests if remaining addresses can cause conflicts with the target address. If they cannot cause conflicts, the removed address will be put back to the set. Otherwise, they will just be removed. In this way, the attacker repeats the second step, and finally, he will get an eviction set. A key observation is that if instead of deterministically mapping an address to some cache set, if we randomly map an address to any cache set, it will drastically increase the difficulty of finding eviction sets. Because theoretically, you cannot find any set of addresses that always map to the same cache set in this scenario. However, we can see that the safety is achieved at the price of performance, because if we want to map an address to any cache set, we will need to check all cache sets upon a cache access, and that is very expensive. So in our PhantomCache, we reach both purposes through localized randomization. In a word, localized randomization is to randomly map an address to one or R fixed cache sets. So upon a cache access, we will need to check all R candidate sets to search for the target cache line. However, even though R is a relatively small number, such as 8 or 6, this can still increase the difficulty of finding eviction sets by 2 to R times. And this means when R is larger than 6, finding an eviction set costs even hundreds of years, which means the attacker can hardly succeed. So how will a cache access be handled in PhantomCache? First, when the physical address is sent to the cache, all its R candidate stats indices will be computed, and all R candidate stats will be searched in parallel. If a cache miss occurs, the corresponding memory block will be fetched from the memory, and a random number P is generated. The P is used to select a set index, a candidate set index, and put the corresponding memory block to that set following some replacement policy. So randomness only takes effect when the new memory block enters cache, which means a cache miss just occurred. In PhantomCache, we compute the candidate set index through a mapping circuit. In the figure, we can see that we introduced a random number sort, which is fixed at boot time. And it is split into two parts, which are used at the beginning and the ending of the mapping function. Why we build our mapping function in this way, there are two reasons. The first is that with hardware efficient hash function, the critical path of the mapping circuit has only 10 gates, and this can cause only a one cycle delay. The other reason we will explain it later. In PhantomCache, recall that we need to compute our candidate set indices. So we need our mapping function units, each equipped with a different sort. We use those function units to compute our indices in parallel. And those R indices are also stored in index registers. So when a cache miss occurs and the memory block is fetched from the memory, we can directly use the random number P to select an index from those index registers without recomputing those indices. However, to realize fully parallelism, a multi-port cache is needed, and this is not very practical because a multi-port cache is very expensive and inefficient. So PhantomCache uses a multi-banked cache to achieve approximate parallelism. But this still causes some problem because multiple candidate stats may lie in the same bank, resulting in a delay upon access. But we do not need to worry a lot about this because the pipeline architecture of modern cache make the delay of successive cache requests acceptable. Here comes the last part of the PhantomCache design. We all know that when a cache line is replaced or flushed, we need to write it back to the main memory. So we need to restore its original memory address. Thanks to the design of our mapping function, we only need to store an extra random number in the cache line, which is about 3 bits. With this random number, we can select a sort from all the R sorts and use it to restore the original memory address through our mapping function. We implemented PhantomCache in ChampSim Simulator. In our implementation, we only touched the LLC module and made PhantomCache a transparent layer between the L2 cache and memory controller. We realized the parallel access mechanism by modifying the LLC queue management policy, where a request was inflated to our sub requests in order to access our candidate stats. We evaluated PhantomCache's performance using Spec 2017 benchmark suite, and the average performance loss over all 20 benchmarks in terms of normalized IPC is only 1.2%, as shown in the figure. The other overheads of PhantomCache are as follows. The logic overhead is around 18,400 GE. and this is less than 2 times of 128-bit AES encryption circuits. The starter overhead is pretty low. It's about 0.5% per cache line, which is 3 bits per cache line. The energy overhead is about 67% extra energy cost. And we know that the energy of a cache consists of 2 parts, the static power and the dynamic power. PhantomCache does not change the static power, but it increases the dynamic power by multiple times. The conclusion of our paper is as follows. First, PhantomCache can effectively protect cache against conflict-based attacks with a minor performance degradation. Second, the localized randomization scheme existing take more than 100 years to succeed. Finally, the overhead of PhantomCache is considered acceptable after precise estimation. Okay, thanks everyone. I'm open for questions now.